Hello, Earth Science students. This is Mr. Holtz. Today, we're going to be talking about carbon dioxide because as we transition into the human impact unit, we're going to be talking about climate change, we're going to be talking about global warming, and the main driving force of that climate change and global warming ends up being carbon dioxide. Carbon dioxide is a greenhouse gas that kind of acts as a blanket to hold in the heat and trap in heat. So, more carbon dioxide means we're going to have more global warming. Um, and we're going to start off looking at, first of all, I've got this picture that is showing the Mauna Loa Observatory in Hawaii. And this is most known for doing astronomical observations and looking at the exosphere, but it's also used to measure things like carbon dioxide concentrations in the atmosphere. So they've been taking measurements for the last 60 years or so, and we can use that to see how carbon dioxide has been changing over the years. So I'm going to transition to this. So this is the activity you guys would have done if we were not doing distance learning. This is called Carbon Through the Seasons, Mauna Loa Observatory Data. And this is looking at Mauna Loa carbon dioxide monthly average concentrations in parts per million ppm. So ppm, parts per million, that's basically talking about how if you have a million particles of things, million particles in the atmosphere, that if you have 1 part per million of carbon dioxide, that means one of those million particles is going to be carbon dioxide. And that's the way that we measure carbon dioxide concentration. So, right off the bat, we can see that there is lots of numbers. And you guys would have had to graph these numbers and analyze what's going on in these graphs. I'm going to make it a little bit more simple for you guys and do it a little bit differently. So, we can see that for the years, it starts at 1959 and goes all the way down to, for this, 2011. So, almost present day. And then we've also got the months January through December. And if you're trying to analyze what's going on with this data, there's not much we can do just looking at the raw numbers like this. We might be able to say that it doesn't look like it drops below 300 or even 310, and it doesn't go up above 325. That's all we can really say. But in terms of the change in carbon dioxide, it's really hard to make any inferences about that. So what I've done is I've actually taken these first 4 years, 1959 to 1962, and put them into Google spreadsheet. And so these are the first 4 years. So this is 1959, 60, 61, and 62 with all of our months. And then the carbon dioxide average monthly concentrations in parts per million. So we're going to see what this looks like on a graph. So I'm going to do insert chart. And here it is. So, based on this, first thing I'd like you guys to do is to analyze this graph. What is happening to the amount of carbon dioxide in the atmosphere from January 1959, which is all the way over here, all the way to December of 1962, which is on this side? Okay, so it's really hard to make any inferences with this. We might be able to say that the carbon dioxide amount isn't changing very much. And actually, if we had taken a look at any other groupings of years, like if I decided to graph 1970 to 1974, it would probably look very similar to this graph. Now, the problem is this graph is not formatted in a way that helps us really analyze any changes. We can see that there's a lot of blank space in between 0 and 300 because none of our data points actually fall in that range. So I'm actually going to see if I can finagle this graph a little bit to make it a little bit more usable. Let's see if I let's do the minimum value 310. So now we can see that there seems to be some interesting things happening. And so we see that carbon dioxide seems to be kind of going up and down. It's fluctuating through the years. And if we take a look at any single year, so January of 1959 to this January of 1960, we say that there's one peak and one trough, one high point and one low point. And that repeats every year. We have a high point and a low point for every year. So what I'd like you to do now is to answer this. Why is carbon dioxide fluctuating? And what type of process, or what process is able to remove carbon dioxide from the atmosphere and might change depending on the season. So there's some process that you guys might know about that is able to take in carbon dioxide, remove it from the atmosphere, and that process might change or fluctuate through seasons. So that's my little hint for you. So as it turns out, the thing that's changing is photosynthesis. So as we go through seasons, we're going to see changes in the amount of photosynthesis in the spring and summertime. when we have more green stuff, more plants, there's going to be more carbon dioxide being pulled out of the atmosphere, going into plants and being converted into food for those plants. And we're going to see during those times a drop off in the amount of atmospheric carbon dioxide. But in the fall and winter months, when plants are losing their leaves and there's less green stuff, there's going to be less photosynthesis and therefore less carbon dioxide being pulled out of the atmosphere and therefore more carbon dioxide kind of staying in the atmosphere. We're going to see kind of a high point for that. So that's what we can see within this 4-year span. But when we're trying to take a look at climate change, we should really take a step back and look at a larger time scale. 4 years is not enough to really make any large scale inferences about changes in carbon dioxide. So we're going to actually jump into this video. This video has a lot of great information. This is from NOAA, I think. Let me see. Yeah, so this is carbon dioxide pump handle 2019 from Carbon Tracker, NOAA. A lot of good information from them. And right off the bat, atmospheric carbon dioxide in parts per million. A couple of things. This is our key up here. We have a red spot, which is the Mauna Loa data, which is what we're looking at in the previous graph. We have the South Pole, so they have a monitoring station on the South Pole, and then there's some background conditions, local signals that are being measured around the world. So these are all areas that are going to be measuring the amount of carbon dioxide, and we'll also see that as we go through time, more monitoring stations pop up, but the main ones we're going to be looking at are Mauna Loa and Antarctica. So on this graph over here, we have the parts per million of carbon dioxide on this axis, and then we have the latitudes of Earth. I'm going to hide this thing. The latitudes of the Earth, so this is the South Pole down here, this is the North Pole, and we got the equator. So we're going to see as the time goes on, we can kind of see how the carbon dioxide is changing, and those results are going to be graphed on this timeline right here. This one's actually starting at 1979. So I'm going to click play, and we're going to see what's going to happen. So this is January 1979, 336 parts per million. And I'm going to pause it right there. And we can see that we have our fluctuations like what we saw when we graphed it in Excel. Again, those are due to changes in photosynthesis. And we see less changes in Antarctica because we can kind of assume there's a lot less green stuff, a lot less photosynthesis, and therefore we're not going to see as much fluctuation. But if we play this just a little bit further, now we might see a trend happening. So what I want you to answer is there a trend now in the change in average carbon dioxide through time? And what is that trend? So it looks like there's a slight increase in the trend, whereas before, if we take a look back at the Google spreadsheet, kind of looks flat. But if we take a look at some more years now, we're kind of starting to see an upward trend in the amount of carbon dioxide. So I'm going to let this play all the way through present time so we can get a sense of really what's going on over a larger time period. So now this is showing right here, October 1989, Mauna Loa sees 350 parts per million for the last time. So what that means is any time after that period, we have not seen the number or the concentration of carbon dioxide drop below 350 parts per million. So now we've approached present day, and this is adding additional Mauna Loa data back to the 1959 date that they started doing the measurements, and that corresponds with the data that we were looking at in the activity. So the data started in 1959. We have data all the way up to present day. Now we're seeing a little bit more of what's going on. So I want you guys to answer about how much has the amount of carbon dioxide in the atmosphere increased from when Mauna Loa first started monitoring CO2 back in 1959 down here, all the way up to present day. So how much has it changed in parts per million? So if we're taking a look at this graph, it looks like it started, and we can actually look back at our data over here. In 1959, it was at 315 parts per million in January. And then in present day, now we're looking at something close to 411 parts per million. So we're almost seeing a 100 uh, parts per million increase in the concentration of carbon dioxide, which, according to this graph, looks like pretty significant change. But then the question becomes, even this time frame from 1959 to present day is on a geologic time scale is still like a snapshot. It's a very small period of time. And is this representative of changes on a longer scale? If we were to look before 1959, would we see carbon dioxide actually be higher than that? Well, let's take a look. Now, the problem is that before this time, Mauna Loa wasn't taking atmospheric carbon dioxide concentrations. So where did the data come from? And actually, the really cool thing is they get data prior to 1959 from ice core samples. So ice cores taken from Antarctica or glaciers. The interesting thing about them is that the way ice is laid down from year to year is very similar to the sedimentation process, where sedimentary layers are laid down in succession and form these rock strata. And we can kind of take a look at those rock layers and take a look back through time as we go deeper through those rock layers. Ice cores are almost exactly the same in that sense, where we can take a look deeper and deeper into those ice cores, and each layer is going to give us a snapshot of different years. And those ice cores will also have basically air bubbles that are frozen, and they will have basically remnants of the atmosphere during that time period. So we can take a look back at ice cores from thousands of years ago and open up those ice bubbles and do some fancy science on them and see what the carbon dioxide concentration was back then. So I'm going to play this video a little bit more, and we're going to see what ice core samples were showing us within the last 1,000 years or so. And now we're seeing something really interesting. So all these orange dots are the Law Dome ice core, and it's going back right now. I stopped it at it's going back to the year 1200, and this is pre-industrial. So this is referring to the Industrial Revolution. So the pre-industrial revolution, the carbon dioxide concentration seemed to hover around 278 parts per million, and then the Industrial Revolution happened in 1850, and we see kind of this exponential growth in the amount of carbon dioxide up to present day. So what I want you to answer is, why was there an exponential increase in the carbon dioxide concentration after the Industrial Revolution? What do you know about the Industrial Revolution that might increase the carbon dioxide concentration? So, as it turns out, the Industrial Revolution resulted in a lot of increase in carbon dioxide because industrial processes, factories were popping up everywhere that was releasing a lot of coal, and that burning of coal and fossil fuels really ramped up during that time, and we saw a huge increase in carbon dioxide concentrations. So, and again, this is still on a small time frame when we're looking at geologic time. So we can take a look further back at ice core samples from before then. So this is still a Law Dome ice core, this orange stuff. Now it's going to show this light blue stuff, which is the Vostok ice core. And now we're going back thousands of years. So KYBCE is thousands of years before current era. I believe that's what that stands for. And so we're going back 100,000 years before current era, 200,000 years, 300, all the way back. And now we're looking at a different ice core, Epica Dome C ice core is this dark blue. And now we've gone all the way back 800,000 years before current era. And so we can see that this is kind of the normal cycle. You might hear people saying that the climate has always changed. That is very true. We can see that the carbon dioxide has changed throughout relatively recent history within the last 800,000 years, that there's this normal cycle. Now, before we talk any further about this, what I want you guys to take a look at is what was the highest CO2 concentration in the past 800,000 years. So take a look at this data. What was the highest CO2 concentration within the last 800,000 years? So it looks like the highest CO2 concentration was right here, just under 300,000 parts per million. And none of these other peaks even really get close to that. And it looks like the low points we have are somewhere between 100 and 200 parts per million. And the interesting thing is these low points are corresponding to what we can call global glaciation or ice ages. So the Earth was covered in ice for the most part in these low points. And at these high points, these are points at which we saw minimal glaciation. We saw melting of ice caps and receding glaciers and things like that. And that was up at, in these cases, 250, 275 parts per million. So if we take a look near present day, before the industrial era, we might expect that based on where this last blue point is, we should see that the amount of carbon dioxide in the atmosphere should be dropping off according to this normal cycle. But we don't. We see that it's increasing exponentially, much past what the normal cycle is. So we're going to talk a little bit more about this normal cycle later on and what causes the normal cycle, but we definitely see a deviation from this normal cycle, and this is what we're concerned about, especially when we say that we tend to see ice caps melting and glaciers receding even at these levels, and now we're up much past that 300 parts per million point. So that's where we're going to end it for today. Thanks, guys, for watching.